Hello everyone. So, we will continue with the unidirectional composites. So, this we have discussed in last class that unidirectional composite were prepared from fibers as a matrix through drape spinning technique, powder coating technique and film stacking technique, and these are tested for their 3-point bending testing and short beam testing. Okay. Now, here if we see the 3-point bending test is mainly for the flexural strength and short beam test is basically interlaminar properties. So, from this diagram if we see the UDCP has got highest flexural strength as well as the short beam test, that highest flexural strength we get from the powder coating, whereas the film stacking technique it results very poor flexural characteristics. So, we can see here that average flexural strength here it is 232. On the other hand, for film stacking it is very low. Okay. The peak load for UDCP was the highest among the 3, as I have seen, I have discussed. It is nearly 3 times higher than the UDCF. So, it is nearly 3 times higher. Okay. Also the modulus of UDCP is observed to be highest. It was hypothesized that the better impregnation of PP powder in UDCP was responsible for higher flexural strength, because the powder is already present inside the structure. So, that is why it is very high. The peak load is highest among the 3 composite, it is 4 times highest. In short beam strength for UDCP and UDCD was observed to be within 18%. So, that is within 18%. So, why is it so? The thorough impregnation of resin within the structure led to higher load resistance, and interlaminar delamination process, that is that interlaminar delamination is restricted here. Okay. So, that is why it gives a higher short beam strength. So, due to the proper impregnation, although the powder coating has got very good impregnation, still the drape spun yarn also shows, hybrid yarn shows the better performance as compared to the film stacking technique. So, here we can see here that this is the drape spun yarn here. In drape spun yarn we can see clearly the fiber zone and matrix zone, it is separated. We can, so this is the fiber zone, cluster of fiber, and similarly in film stacking we can see that matrix and fibers are totally separated. This is fiber, here it is a matrix. But in case of powder coating, the penetration of powder, penetration of matrix is very good within the reinforcing material. They are uniformly distributed. That is why it results very good flexural strength. So, scanning electron microscopy shows that the carbon fiber, so F and matrix, they are very good intermixing is there, as I have already mentioned. Okay. Same powder coating process can thus overcome the challenge of using high viscosity thermoplastics. So, that is why the problem of thermoplastics are, the problem's main problem is that due to the high viscosity, its penetration within the reinforcing material is poor. It needs very high pressure and it also results a void content. But the powder coating is the solution in that direction. Microcomputed tomography of the composite after the flexural testing was done here. In this diagram, the matrix was represented by green color. This green color is matrix and black color is the carbon reinforcing material. In UDC-D, which is made from Dreyfus Hybridian, we can see here this is the top side during the bending study, 3-point bending. This is the top side. So, in 3-point bending, this is the composite base and here it is a bending. So, this is the top side is shown here and this is the bottom side, this is the bottom. So, in top side what we have observed, there is a significant fiber breakages are there in the compression side also, and bottom layer undergoes the tension here. Okay. The not that much breakage took place here, that means there is no proper bonding is there due to relatively higher void content. So, this at the top side, at the compression side, the breakage is due to the pressure, that damage of fiber, but at the extension side there is not significant breakage was observed. On the other hand, if we see the powder coated composite, the breakage was there both in top and bottom side. That means, the load is being shared by the reinforcing material at the back side also. That is why it gives very high flexural rigidity. If we see the film stacked composite, absolutely there is no breakage of carbon fiber, the reinforcing fiber. What does it mean? There is a clear sliding between the carbon filament and the matrix. So, that is why the proper load bearing is not there. So, this has been explained here, I have already explained. So, this indicates partial transfer of load between carbon toe and PP matrix for UDC-D at the other side. Back side there is no transfer of load is there, and UDC-P, that is a powder coating, we have already explained that its proper impregnation is there, that is why proper load sharing is there, that is which result very high flexural strength. And here simply its sliding is there, that is why there is no load sharing. or very less lead sparing. Now, you can see schematically here this is the fiber and powder coating is there, that is a proper penetration of the proper penetration of matrix component is there inside the carbon toe. This we have already discussed here. For film stacking composite, the same image clearly indicates that matrix rich and matrix starved portion, that we have already seen, okay, layer by layer. So, higher viscosity of polypropylene film as well as low melt flow index does not support impregnation of polypropylene into the various layers. So, that is these are the different reasons. And our last experiment is that the investigation of the mechanical performance of carbon polypropylene 2-dimensional and 3-dimensional oven composites. So, that from the drape spun yarn, that is a hybrid yarn, and from hybrid yarn top reg and the powder coated top reg, we have produced 2D oven fabric and 3D oven fabrics, and from there we produce composites. So, to prepare textile preform through 2D and 3D weaving for thermoplastic composite using powder coating and drape spun hybrid yarn. To consolidate the produced fabric in the compression molding process and to produce 3D composite laminates. Now, from 2D fabric we have to produce 3D composite laminates. Here what we have done, we have used 3 layers of 2D fabric. This is 2D oven fabric, 3 layers to keep the mass per unit area same as that of 3D weaving, 3D oven fabric, and to investigate their properties. Now, let us see the plan of work. So, we have used 2 technique here. 2 techniques are drape spun hybrid yarn and powder coated hybrid top reg. So, powder coated top reg is there, then heat setting of hybrid yarn is required. Powder coating system involves the heat setting. So, we do not need heat setting here. Then we have weaving. So, we have woven in 2D fabric and 3D, we have used 2 different structures, orthogonal 3D and angle interlock 3D for both powder coated and drape spinning yarn. And then we have used compression molding. For 2D plain oven composite, we have used 3 layers as I have mentioned to maintain the mass per unit area, and then 3D composite, 3D oven composite in using the compression molding. We have studied the mechanical characteristics and also as well as matrix distribution. In mechanical, tensile, bending, notch impact and mechanics of crack propagation, this we have discussed, and microcomputer tomography. So, what we have done? We have studied 2D versus 3D. So, orthogonal effect of weave we have studied. Then what we have studied? Effect of fabric structure, that of 3D oven fabric, that angle interlock and orthogonal, effect of weave here, then effect of hybrid yarn production using powder coating and drape system, and effect of hybrid yarn production of both for 2D and 3D. These are the factors we have studied here. So, hybrid yarn production, drape spinning, that we have already explained. After drape spinning, we have what we have done, we have here we have treated with heat treatment, 2 heaters were there. So, heater 1 and heater 2. So, thermally treated drape spun toe frag is produced to improve the weavability, otherwise there will be fraying of the sheath fibers. Okay. That is why to improve the weavability we have used. So, these are the various steps or reasons for heat setting. So, for better weaving performance we have to set the heat setting. So, before heat setting the SEM image, and this is after heat setting, partial melting is there. We do not need complete melting will increase the flexural rigidity, that will create problem during weaving. So, partial melting is required to have a better flexibility also, and electrostatic spray coating, that we have already explained. So, this is used for powder coating, and then we have taken these yarns for weaving of 2D weaving and 3D weaving. The 2D weaving woven structure is here. So, it is a plain woven fabric, one up one down, and this structure is that the 3D angle interlock, where the we have weft yarns, these are the weft yarns, and warp yarn, there we have 2 types of warp yarn. One is the staffer warp yarn, which are almost straight in alignment, and another is the binder warp end. Okay. This structure is it is a 3D interlock structure and 3D orthogonal structure. Here again the yellow color thread are the binder warp thread, and this blue are the stopper warp thread, which are little bit straight. These are the structure, one by one up one down. Okay. Peg planning is there, and peg plan for the orthogonal structure. This is the peg plan. Okay. Detailed peg plan is there. Here in orthogonal structure you can see here the binder yarns, binder warp yarns, there it has got very high crimp. Okay. So, if we apply the stress and the warp direction, the mainly the staffer warp yarns are straight, because as here it is stopper warp yarns are stressed because of the fact that they are almost straight. Similarly, the angle interlock, these are the peg plan. This binder threads are little bit angled. So, here you can see the crimp is relatively lower here, okay, crimp of the binder yarn. So, warping and weaving was done using CCI loom. This is the production of fabric. Here this is the beam for binder warp yarn, beam for staffer warp yarn. There are 2 types of beams are used here. and the loom is a rapier type loom. Now, if we see here, this is the weaving of the 3D fabric. A small room, one is binder, another is the for stuffer work. Finally, we get the 2D and 3D fabrics. Now, the abbreviations of the composites were, this is 2D WCD means 2 dimensional, made of 2 dimensional fabric, woven fabric, composite made from drape yarn. Okay. And 2D WCP from the powder coating. Similarly, 3D AC, angle interlock and orthogonal structure. In this way, we have prepared samples of 6 different samples were prepared. Now, 2D fabrics are 3 layer. So, ends per inch, peaks per inch is given, and here the mass per unit area is almost very close to each other. So, they are equivalent. Okay. Fiber volume fractions are almost equal. So, they are almost same, very close, around 50 to 55%. So, it is a fraction, it is not a mechanical characteristics. We have done tensile characteristics here using universal tensile machine, okay, following the ASTM standard test method. Now, if we see here the tensile stress, it is highest in case of 2D woven composite made from the powder coating, and 3D from angle interlock, it is followed by angle interlock, and then 3D orthogonal is the least strength. So, basic reason is that due to the very high crimp, and these are tested in warp direction, very high crimp in the binder threads, they are not carrying the load, but in case of 2D all the warp threads were carrying loads simultaneously. Here the loads were carried only by the stuffer threads, which are relatively less crimped. We can see here both the modulus and the tensile strength are higher in case of 2D composite, 2D woven composite. 3D composites are less. This picture shows that, and but if we compare the drape with the powder coating, always powder coating is higher than drape for all the structures. This is mainly due to proper impregnation of powder or a matrix within the reinforcing material. Here it is a tensile modulus, the same trend is observed here. So, the values of the average tensile strength as well as the modulus obtained are represented here. So, this we have already seen here that 2D is higher. So, the strength of the 2D composite was found to be 36% and 45% higher than angle interlock and orthogonal respectively. Similarly, the composite produced from powder coated top rake, the maximum stress of this. So, for this is for drape spun and the powder coated, the trends are same. As I have already explained, on loading the 2D composites, all warp threads they share the load, but in case of 3D composites only the stuffer shares the load, as the binder warp had undergone large folding or crimping during weaving. This is the large folding is there. So, they do not share the load, that is why the 3D fabrics shows very low modulus and strength. So, value of crimp, so for angle interlock it is a 7%, okay, and the binder thread, and 30% for orthogonal. So, that we have seen. But upon stretching beyond maximum strain of 1%, carbon breaks. So, that is why the in 3D composite the binder threads they do not take part in loading. The values of crimp of binder warp threads, as we have seen here, 7 and 30% respectively. So, in addition to the fact that average strength of 3D angle interlock composite was higher than 3D orthogonal, the difference was statistically insignificant. This difference was statistically insignificant, although it is little bit higher. So, the same pattern was observed for drape spun yarn, hybrid yarn, that composite made of drape spun hybrid yarn. So, this is the same pattern was there given, okay. These are the for powder coating and these are for drape, okay. Now, let us see the mechanics of crack propagation. So, if we see the crack propagation, so after the tensile breakage we have studied the crack propagation here. In 2D crack propagation was not in straight line. Similarly, here the crack propagation was not straight, but this one is the orthogonal. B3 is the staffed warp pull out. You can see there, it was noticed that the line of material separation in 2D composite and 3D angle interlock or not straight line, unlike this is a straight line. This can be attributed to the fact that the here this is the line of the optical image of fractured, here it is a fractured side. Now, the here material separation line it is straight, here material separation line is angle. So, due to the structure of the base fabric, the characteristics of crack is there, it shows the similar characteristics. Okay. So, what we can observe, the crimp and pattern of consecutive binder wave determines the strength as well as the strain of the composite. Okay. That is a binder, and in the last part we will discuss the flexural properties of this composite made from 2D and 3D fabrics. Now, here in 2D we can see here again the bending rigidity of 2D is higher than the 3D fabrics, but the powder coated fabrics were higher little bit than the drape. The reason we have already explained, flexural strength, it shows the similar trend to that of the tensile. The reason is almost same here. So, overall the 2D composite shows better flexural strength and modulus as compared to 3D fabrics. This is attributed to the fact that higher number of load bearing toe brake are in line with the direction of tensile and flexural strength, flexural loading for 2D composite. So, that is the basic reason here for having higher flexural and tensile strength of 2D composite. Although 2D composite here we have used 3 layers of fabrics to make it equivalent. But coming to the impact notch impact test, where we have used IZOD notch impact testing, here the impact method we have already explained earlier. Now, if we study the tomography, computed tomography, we can see here it is a 2D drape and 2D powder coating. This one is with matrix and fiber, this is with matrix and fiber. Here only the fiber without matrix and sectioned slice showing the fiber breakage. Here it shows the fiber breakage part. Okay. Toe brake, this is for 3D oven angle interlock, earlier it was 2D, now 3D orthogonal. Here we can see here now 2D and 3D impact strength. Now we can see the impact strength of 3D orthogonal is much higher than the 2D, although tensile and flexural strength was high in case of 2D oven composite, but in case of 3D orthogonal it is very high, followed by the 2D angle interlock Similar trend is there for powder coated composites. Now, you can see here. So, this is the powder coated 3D orthogonal composite, it is high. So, 3D orthogonal composite absorbs more energy than 2D by approximately 45%, while 3D orthogonal made from drape yarn, it is again approximately 47%. Shows that the image indicates the failure of the specimen as a result of breakage of warp threads in 2D fabric composite, and the breakage of straight stuffer warp threads in 3D angle and orthogonal. Now, here breakage is there only in 3D fabric, only in the stuffer warp thread, but the load is can be carried by the binder also. This is the same image you have seen. So, that is why the energy notch impact energy is much higher in case of 3D woven composite. And if we compare with the drape spun yarn, composite made from drape spun and powder coated. So, powder coated is little bit, it shows a little bit higher in tensile strength, typically 11 and 20% respectively, as we have observed here, and this is basically due to better impregnation, as we have already explained here, better impregnation in case of powder coating. So, the melt flow distance refers to the distance that matrix has to travel within the reinforcing material, and melt flow distance is required is low in case of powder coated. So, in drape spinning process, the carbon fibers are present in the core. So, melt flow distance is required is very high, and that is why proper impregnation is not there. So, on the other hand, the electrostatic spray coating, it has not changed the elliptical cross section of the carbon. So, here it has become circular, and this is the carbon toe. If we see, it is carbon toe without any matrix, but once we produce the yarn, drape yarn, it has become circular. So, the flow distance need is higher, but in case of powder coated toe, the shape remains almost same. So, flow distance required is much lower here. This has been explained here. So, powder coated toe preg based 2D and 3D composite, including 2D woven composite and 3D angle interlock composite, is that shows that 11 and 21% higher flexural strength than corresponding drape based composite yarn. So, despite higher viscosity of PP powder matrix than PP fiber, PP fiber matrix has got very lower viscosity, and PP powder we have seen that viscosity is very high. Despite that fact, better impregnation of powder coated takes place, and this proves that manufacturing process of powder coating is highly advantageous. Now, the final comment is that the composites made from powder coated toe pegs show better matrix impregnation and less porosity compared to composite made from drape hybrid. So, hybrid shows little bit higher porosity, void content was there. And the use of powder coating technique helps in overcoming the disadvantage of hybrid type yarn, and from our basic study we are very confident that the powder coating has got its bright future after eliminating few shortcomings like speed of production, that volume of production, or some factors. We need commercial grade machine also. So, we are very hopeful. Now, I will finish the topic of composite here, and these are the references we have used from different sources. So, there are many other areas left, but it is not possible to cover everything here. So, we have here it has been tried to cover to get the broad overview of the area of technical textiles. I hope you have enjoyed this course. Thank you.